Hello everyone, welcome to this section. I'm Ta Wai, a software engineer at ARM, and now I'm working on VIXL project. This is our outline today. First, I will recap what VIXL is, and then go through our main part of this talk, what feature has landed in VIXL and what is coming next. VIXL is open source ARM v8 runtime code generator library. You can find it in Git, Linaro Git repository. Just search VIXL plus Linaro and in Google, and you will get the link. Now, VIXL is considered mature since it has already deployed in Android Google runtime compiler, Mozilla Firefox browser, and Google V8 engine. VIXL has four main components: assembler, microassembler, disassembler, and simulator. VIXL's instruction support cover core AArch32 64-bit instruction set with latest V8 extension, and neon floating point instruction with half, single, and double precision data type, and SVE, what we are working on. VIXL intend to support the lowest exception level, ELCO, for running user mode application only. Assembler. Assembler is used to generate ARM v8 assembly at runtime. It provides a programmatic API, which is written in C++. These APIs one-to-one mapping from API to Google V8 ISA. The input of APIs such as register, memory, and constant are all parameterized. I think it is intuitive to use. This is an example. If you want to generate move instruction using VIXL, just instance assembler object and call the corresponding API like that. The second operand of the add instruction stands for left shift 2 bit of the value in register X2. Because it is C++ code, so you can customize your code gen logic. For example, you can adding a for loop like that to generate multiple load instruction that load the data from different memory location to different destination register. It's quite simple to use. And we also provide a debug feature to check immediate and code size validity. And it is useful because each instruction had its accepted register type and constant constraint. We know ARM 64 instruction is 32-bit fixed size, so it has encoding limitation. The limitation not only in the encoding width, but also in the encoding format constraint. And microassembler abstract away the limitation. Let's see the example. Assembler doesn't allow to move a constant that wider than 16-bit to the register by the move instruction, like that. Of course, you can do it by your hand, split it into small pieces to fit in the encoding width, but or alternatively, you can generate using microassembler API to do so. And note that a microassembler inherits from assembler, so you can use both API interleavely at the same time during code generation. In terms of abstraction, for example, in ARM64, register 31 can be stack register and 0 register. microassembler is able to generate correct code for you indicate. And we also abstract immediate and offset, not only for integer only, it works for floating point too. In addition to flexibility and convenience, microassembler is useful even if the constants are expected to be incurable, because microassembler provide safety net, such as code buffer checking, instruction scope checking, and more importantly, it provide scratch register management. For example, users don't need to manage the scratch register anymore. Just use our API like include, exclude to define your scratch register pool, and then using them by acquire and release method. At last, sometimes people may not sure what exact assembly should be chosen to generate. As microassembler has ability to pick up the most appropriate instruction for the input you gave. It's quite convenient. This is disassembler. Disassembler can print all instructions emitted by VIXL assembler, like that. And the output is it's compiled with ARM64 spec. And this is modularized, so it is easy to use. Just instance the disassembler object and skip it the instruction stream in binary format, and done. Simulator. Simulator can run all instructions emitted by VIXL assembler. It is instruction functional, not cycle accurate. Let me go through this diagram by a few steps to see how it works. Once simulator has a generating code, the decoder will get involved to interpret what coming instructions are, and then dispatch them to corresponding execution logic for execution. This is our new decoder. We added this year. We substitute the switch-based decoding approach by the tree-based approach, giving more manageable and maintainable. As you can see, there are logics for core ISA, Neon, and SVE, alongside their register class and memory. Now, VIXL simulator has come to be used a variety of purposes. So we think disassembler has become the most useful tool of VIXL. There are some practical use cases. For testing, simulator allows user run their ARM64 software without having to run on real ARM target. This is not only very useful in CI system, but also for manual tests run by individual developer. For debugging feature, simulator can trace every instruction is executed, every register memory is updated. It is very useful when debugging. It allows user to look back in the history from the point of a crash. And the next is a stack analysis. We have internal prototype, trace building prototype to allow user to step forward and backward of the execution to see reconstruct machine state such as register and stack register state. And the last is algorithm development. Since since simulator has debugging and tracing feature, so developer can using standalone simulator built to prototype their algorithm or tune their high performance library and so on, and then implement them after ensuring the runtime behavior, their runtime behavior is correct on a simulation environment. This is what exact trace output from the simulator. We also provide a handy API to let user to instrument to their code to see their runtime behavior of their code. Or either you can use this option to enable the tracing in simulator. We will update, we will show the people only the relevant register or data or memory is updated in each step. This is the overall picture of VIXL. Programmer write code in API, and note that microassembler doesn't emit code directly. It always goes through assembler, and then generate code. Once we have a generated code, we can run on ARM machine natively, or you can run it on our simulator, either on AArch64 machine or ARM machine. Okay, this significant feature has already landed in our VIXL. We're starting at 3.0.0. We adopt semantic versioning, and we will release the new package in that way. The number here means major, minor, and version and patch version. So the user want to get the breaking feature from VIXL without breaking their code. I think getting the minor version release is a good choice, or user can get the most advantage in each major release. We also implement CPU feature management and detection, and release part of V8 extension we have done in this here. I will go through it very briefly in the following slides. Okay, in terms of feature management, a part of VIXL user want to control what CPU feature are available for their purpose. So we design an API for them to manipulate the feature set regardless of what the actual ARM machine they have, like this. And in terms of feature detection, the other part of VIXL user just want to enable every CPU feature on what their platform has. So, but this is the implementation isn't very obvious. So we managed to decide an API to implement it for them. Okay, and then I will go through very quickly on what extension we have done. We have done pointer authentication. This series is used to for software stack protection and control for integrity. In VIXL, it's very easy. For example, you can in function block using PAC API to use a linking register and stack point to calculate, to compute the signature, and at the end of function, you can use this AUT API to calculate, to verify the signature before using that pointer. BTI is another security feature we have added. The basic idea is that BTI enforced in direct branch can only go to the code location that are marked as valid before. In this example, in VIXL, use by this API with BTI ID telling the simulator or showing this label, this address is a valid jump target. We also support FP16 in VIXL on Neon and SVE extension. To my knowledge, FP16 is widely being used in quantized deep learning model. And we also provide a utility to let user to easily construct FP16 representation like that. We have a signed and unsigned dot product instruction. This is a very easy example. Using this API, we will calculate as right side of this picture. It is done the dot product of 4 8-bit elements in source register and then calculate them into 32-bit length in destination register. We also provide RCPC. Okay, let's go through. And LSE used to reduce runtime overhead in back system. Here is an example to see how to use compare and swap instruction. Quite simple. And provide JavaScript style conversion. And if you may be interested in this instruction, if you deal with complex number calculation, you need to just place the complex number on the corresponding position of the source register, and then just call the complex multiply and accumulation instruction. Okay, at last, we spend majority of time to adding support SVE instruction. SVE has 32-bit Z register and 32-bit 32 P register. And you can see on the right-hand side, the lower bits in each lane of the P register indicate the corresponding lane is active or not. SVE is scalable and configurable from 128-bit to 2048-bit. Keep in mind, our VIXL simulator is also configurable. For this purpose, we managed to redesign our register classes, execution logic, and debug utility to support that. And in VIXL, we also follow the SLA vector length agnostic programming spirit. So VIXL users don't need to care the vector length when they are using VIXL to programming SVE program. Here is our on developing branch. You can get it for preview, and we hope the major useful functionality can be available by Q4. This is an example to see how we using VIXL to coding the DAXP kernel code. We also support register tracing and memory tracing for SVE. We only print out the relevant part to the user because SVE vector length can be very large. So we just print the pretty reading form. And the last, this is our feature we will going on. For example, we want to support a new memory coloring, and we want to moving forward to C++ 14, and solid our code by more static analysis and code coverage. Yeah. Okay. Thank you. Any question?
Yeah, thank you. So I wonder now, how popular is VIXL right now, and how many projects are you actually using VIXL?
How many projects? You mean external or internal?
External public projects.
To my knowledge, is Arch, Android, Google Runtime compiler is using VIXL, and Mozilla Firefox is using our microassembler and assembler, and Google V8 is using all of the part of VIXL.
Okay, thank you.
It's also used by HHVM, the Facebook, HackVM. It's a more server technology.
Oh. Okay, thank you. Okay, thank you.